Hello, nice to meet you. Thank you very much for attendance. So let me introduce Bruno Mesnet, most of you know him perfectly. He has been introducing this HLS activity into the SNAP that is already 3 years old now. So it's a very good story that we have also with our colleague Lu Yong that you have been able to follow, and the China team and also US team. So it's really a good cooperation that we have within IBM. Myself, Alexandre Castellane, I joined Bruno's team 2 years ago. And last year we were very lucky to have Fabrice helping us also on the cloud and testing activities. So we will present to you a new way, let's say, to consider the today AC922, but the coming servers that IBM is providing, and also any server that take place into the OpenPOWER ecosystem. And we'll see how we can set up a system that we are working today with two major actors that we cannot mention, but it's not very difficult to understand who we are working with in terms of data acquisition. So this is really something we are working on. We have several bricks, and we have a very good feeling that all these bricks can work together in a system. So let's take an acquisition of an image, which can be not a regular video image with RVB streams, which are sometimes already addressed by Fpga cards, but let's take a high bandwidth generation system which provides us pixels, yes, let's say pixels on which we have several items, several processes that we would like to achieve on these pixels making like a frame or an image. The first thing that we would like to do in this generic case would be to manipulate these pixels, because they might not be all in the same range, they might not be all in a good format, they might be in a given format that needs to be processed. And usually people, for years, they were thinking processing things in GPUs. So that's really the first thing they have in mind. And there is a tendency to feel that, and this track today in this room is really showing that many muscles calculations, very raw and I should say stupid, but very easy calculation could be done very quickly on Fpga, directly manipulating the data at the source without boring the server with useless bandwidth utilization that we can avoid. So this would be the first process we would like to do, and we'll see how Fpga can help. Then we'd like to be able to process the obtained images, so they would be ready and reformatted. They should be ordered. All pixels should be at the right position, so pixels could come in a strange way. They could come in different position due to the different lines or different subsection of an image, and we would like to sort that. So then we feel that GPU can be a good candidate for that, for sorting out eventually and removing pictures that are not very good. And hopefully with the OpenPOWER and P8, P9 processors, we can have the hope to compress the images that we have obtained after they have been tagged or sorted, and hardware compression will be a very good candidate for that. So uniquely, we have a solution that can process everything into a server. So the question is, can we do it? And we'll answer by a good yes. So the first step, as I said, would be data acquisition. We will see how we can use CAPI and OpenCAPI to process a huge number of data coming. We'll see through HLS and SNAP and now OxyAxle how Fpga can be much more easily programmed than before. We'll see how we can make advantage of what Lu Yong introduced already, the unified memory to make communications between this Fpga world and the GPU world that's coming. And we'll see how the hardware compressor can be used eventually to process the high bandwidth data that we collected. And we'll see how CPU, GPU bandwidth can be very useful in this case. So let's take the first step. We will go into the details of this. But the first step would be to collect a huge number of data thanks to the cages that we have here on basic Fpga card. This is a 9H3 Alpha Data card, which we take as an example, because Alpha Data is a very good partner for years now. It offers 200 gigabit Ethernet stream in, and we can also have a 22 gigabyte, so 25 in and 22 in and out to discuss with the CPU or the host memory. So thanks to TLX DLX that we have in OpenCAPI layer, for the third layer of CAPI, we will be able to communicate very quickly with the host memory and manipulate things directly at the source in the FPGA. Then, thanks to this shared memory, let's say shared memory, we could organize that this guy is instructed to put the data not anywhere in the host memory, but at specific locations which can be shared by the coming GPU that we will have here. So the CPU will see this memory, but the advantage is that this guy can see also the same memory as the GPU that's coming here. So the data would flow without borrowing without requiring any instruction from the CPU, could flow directly from the FPGA through the host memory to the GPU for processing and eventually sorting or throwing away bad images or whatever you need to go. It's really a generic case we are working on today that can be applied to different solutions. And hopefully at the end, because there is a hardware compression capability inside the P9, we can profit by this to have a very good results on the compression here that we will see at the end of the presentation, this part. So the AC922 is a very good candidate for that because it offers a 2-socket machine offering one OpenCAPI and eventually 4 GPUs if we don't have OpenCAPI, but 2 GPUs and 1 OpenCAPI. We'll see in a minute how things can be organized. We can also rely on 3 CAPI2 slots in the case where the bandwidth is not sufficient, is not high enough to justify OpenCAPI utilization. We can be satisfied with CAPI2, which is very nicely and very stable on this machine. Okay, and that's another option that we are studying today with the machine that IBM is announcing for late this year, which is a machine that could host several OpenCAPI and also PCI Express-based T4 GPUs. This example of the machine that Greg can show you at the OpenCAPI booth. So you can have a look at the first generation of this machine. It will give you a sense of what the second generation of the machine could be when you can get it, let's say, early 2020. In this case, we can load the machine with we can hope to load the machine. This is really advanced information because it's not plugged and the machine is not working today with these cards, but we could double the bandwidth that we could input here, and this could provide a very good T4 GPU process on the machine itself and still getting access to this compressor. So we have an advanced information here. We were not authorized to mention that this machine would have a name which would be almost the same as AC922. Okay. All right. So for the data acquisition, that would be interesting that we do you want to go ahead, Bruno, from there? I give the end to Bruno.
To change the voice, it's better for you. Yeah. Okay, so let's have a look to the data acquisition. So first of all, you have a FPGA card. It can be any of them who are not vendor attached. Okay. So this one is an alpha data. You can have old Nalatec, now Bitware cards. All will depend on what you want to enter and what you want to process and how much memory you want on it. Okay, all of these can be enabled on Snap or OCXL. It will all depend on if you have this connector or not. Okay, so what is a FPGA card? It's made of 3 different types of things. One is FPGA. You can have some memory bandwidth here, high bandwidth memory, sorry, here or on the card. And you have some IOs. Some of the cards you can find will have a huge memory on it with no IO. You can have all the different configuration. You choose the card depending on what you want to process. Okay, and you will find a very small flash to host the code, host the code for the FPGA. Okay, so what is a FPGA? I'm sure I will not dig into this one too much because all of you may be aware of that. In a nutshell, it's just a huge array of logic. So it's no code is working on that, is running on it. It's logic defined, designed, connected just for your algorithm. But you can also find some much more complex FPGA with some ARMs in it, some processors, mix of processors and logic, programmable logic. So we are using today only these ones, but we could very easily use FPGA with some processor embedded. The other point is use the different use or choose the FPGA card depending on the resource you need. So you can find some very high bandwidth throughput cards, or also no bandwidth but high memory on it. So sticks of 1 terabyte or cables to go to M2 to U2 drives, and you can find that connected to the NVMe SSD on the front panel of the server. Okay, so depending on if you take a card using the PCI Express Gen 3 or Gen 4, you will have 14 gigabytes per second. If you use the OpenCAPI links, you have much more than that. Okay, so let's try to focus a little bit more on going through the flow. Speaking about Cappy. So we spoke a lot about Cappy. We maybe should have started with this presentation, but well, Cappy, we are today at the 3rd generation of Cappy. So some of our competitors, I would say, are announcing that they will come also doing some coherent memory. It's an announcement. We are already at the 3rd generation. So just to understand what is Cappy, well, the coherency. Think about redesigning your server. Today, you are thinking a process running on a CPU, accessing some memory, and accessing some some IOs elsewhere. Just think about adding, I would say, a new core, but designed for your algorithm, accessing also to network and to disk, and sharing the host memory without any CPU involvement. It's just we are changing the paradigm, meaning that the host memory is the middle of the server. So your FPGA card will access the host memory exactly with the same right than any cores on the CPU. This one will be master, thanks to Cappy. It's not anymore a slave card like all the one you can find on PCI Express, where you need a driver, a software driver. The driver is a hardware driver, which is embedded in the chip. So you access the host memory through this hardware driver. Okay, so this means that you are able to put 1, 2, 3, N cores specifically designed for your algorithm, which is much more efficient than any CPU that will try to understand the different instructions you are sending and try to give you some performance. Okay, so just to explain you what is Cappy, that's the normal thing. You normally put the function in your FPGA card. This FPGA card is accessing the data or the network. When you need some data from the host memory, you just need to use a driver and then to send all the data to the FPGA so that it can be processed. You understand that the bottleneck today is this one. We need to send the data, and the F function will have to manage with the data coming in. What we change with Cappy, okay, sorry. What we change with Cappy is we move this this link to another link, meaning we are using a proxy, Cappy proxy, which is the hardware driver. Okay, this means that this function is able to access directly to the host memory. So I'm cheating a little bit because I'm not using this one, but we are using this one. Meaning so that the function is able to go and read and write just the data he needs. We don't need to transfer everything on the card. He's just accessing this. And as Lu Yong told you a bit earlier, we did the test, trying to have some data gathered, scattered in the memory, and by just sending a pointer where all the different pointers are and accessing them, we are all saving the driver time, and this is confirmed. Okay, so the good thing is that now with Cappy, this function is not a slave anymore; it's a master. We can have multiple users because there's no more driver, meaning that multiple process can be connected to multiple functions. So one card can be used by different users. One thing also very interesting, and for the coder, if you have in the application an address 1000, you can just use the same address 1000 in the function, and you will point to the same area, meaning that you are able to share. You are going to share this area of memory, and this is one of the explanation. If you have looked now to the FPGA cards we have, sometimes there's no more DDR, no local memory in it. So my question was to Alpha Data, why don't you have any more memory on the card? And they told me, well, we have the host memory. We have so low latency between the card and the host memory that we are using the host memory as the local memory. And say, oh, okay, so it's changing really the paradigm of all that. Yes, the FPGA is now master, and this changed a lot of things. Performance, as I told you, we are at the third generation. The first one was with P8. It was just, I would say, to show how things, what we could do with that. It was a new concept, a new thing. We had some performance, some numbers. We have now on Power 9, Cappy 2, which is still on PCI Express Gen 3 or Gen 4. We are supporting Gen 4 today. We are able to have measured numbers very close to the theoretical bandwidth. And we are able, on the same machine and same server, to have either Cappy 2 on PCI Express or OpenCAPI with these numbers measured. So all these are real numbers. We have measured them. We're not relying on marketing numbers. So, well, I'm not relying on marketing numbers. I'd like to test them. So these are real numbers tested, and we can show you how to do things. So yes, 22 gigabytes per second measured. We just got the numbers with OCXL in the middle. We are near 22 gigabytes per second, so we still have a good thing. And this is a total latency, so back and forth. So from the FPGA to the memory and back. These numbers are quite good numbers, useful for all the high-frequency trading companies, which see that and say, oh, that's good. We are cutting by 2 the latency. So this is quite something that can be a good point. Okay, so how do we program this animal? You can do VRLog, VHDL if you like that. Well, it's like coding things in assembler. Now we have done a big step. We are able to code in C, Python, and everything on a server. Here we can now fully program a FPGA using C or C++. Okay. Hopefully we have some tools, some compilers. We are not, and we are able to have almost the same results and even better than Verilog on VHDL, which is maybe surprising for VHDL guys, but this is true. I tested it. Okay, so this means that you have a way now to program this chip using C, C++. I'm not talking to web designer. I'm talking to I would say software coders, low-level software coders who knows what is a memory, who knows what is a process, and who knows how to deal with things. Well, I'm not putting any containers in it yet, but maybe next generation. Okay, so we have put different names here because in IBM we love acronyms. Nobody knows them except us. So that's good. We're able to speak together, but not with the world. So we try to put everything. HLS is high-level synthesis. It's a Xilinx tool. We have embedded in the different Snap or OCXL framework. You can use any other HLS provided by Cadence or any other guys. They are just, quote unquote, translating C to VHDL. And that's all what they are doing. Okay, it's a translation, but a parallelization and an analysis of the code, so it's not just a translation. OCXL is now published. You changed that, good. It was, okay, good. Via OCXL, all the names, I think I spoke about that. No need to dig more on that. Okay, so the Snap concept or the OCXL concept is quite simple. It's you have your server with host memory, CPU, and the network and the disk. You are just going to move a function, which we call here an action. So you can have multiple functions in the FPGA. And this FPGA will have the ability to access the network or the disk, and the CAPI will have an ability to access the host memory directly. So if you are accessing the host memory, you can also access any GPU memory. And I'll come back in a slide or two on this point, which is very important. And to ensure that the user doesn't need to know how to code a read and a write to DDR3, DDR4, HBM, or any protocol, specific protocol, we have hidden all that into the Snap or OCXL framework. Everything is open source, so you can have access to the source code of that. But the goal of this is to have everything transparent for the user. As we told you, you were designing things on Snap or CAPI 1 or CAPI 2. You will be able to move things to OCXL without changing a line in your code, which is quite a good thing. This means that if you change from one card to another, from one CAPI technology to another, you don't have to change anything. You just have to recompile thing with the new thing. Obsolescence is an old thing now. If you remember, moving one thing from a FPGA to another one was a rewrite. You had to rewrite everything. Now you can just move things, which is quite a good thing. Yes. Well, nearly. And the other thing is we have added the Vivado HLS tool, which means that you can write now things in C and C++. Okay, one thing I wanted to come back on is the host GPU unified memory. So Alexandre told you that FPGA is able to write data somewhere in the host memory. And very often, the GPU needs to get this data. So you can do that in one hop or two, okay? So we did the example to see if we were really saving time or not. So the first thing is, normally you take data from FPGA, you push it to the host memory, and then the NVIDIA driver, for example, takes the data, do a NV memcopy. CUDA memcopy, thank you. Does a CUDA memcopy right to the GPU memory. So the idea was to try and do something different using a unified memory. So we allocate some memory from the GPU. We take the pointer, and you give this pointer to the FPGA so that he is able to write directly to this memory, wherever it is. And this is interesting because the FPGA has no idea if he's writing here or in a unified memory. He has a pointer, he writes to a pointer, which is very good because if you change from one configuration to the other, you have no change to do in the code of the FPGA, which is interesting if you change from one server to another, for example. Exactly the same thing if you want to do that on OpenCAPI. So normally you take FPGA, so just one thing, you cannot put NVLink and OpenCAPI link on the same socket. Okay, so that's why I removed the GPU. So, and this is just a firmware problem. It's not a hardware problem, it's a firmware problem. Firmware limitation, it's not a problem, it's a limitation, that's right. Okay, so if you take from OpenCAPI, sorry? A feature. So if you want to, if you have some data to push to the GPU, normally you take FPGA through the NVLink, through the OpenCAPI links to the host memory, and then a QDMM copy to the GPU. And what we wanted to show is that we are able to do that in one operation. Okay, so very simple. I took the code. This is the code we used. First of all, you have FPGA writing data to the host memory, and then the GPU reading it, and then the GPU computation. Here is very small, but it can be very large. It's not this problem we were looking to. And then back writing to the host memory, and then reading it by the FPGA. Even if the FPGA is able to read and write at the same time, we are just serializing things. Okay, and this is what is done by the host memory, by the CPU, attributing a device, doing a QDMM copy, that's this one, the GPU reader, and then doing that's just adding, multiplying by 2, so something, and then sending back the result, and then synchronizing things. So what we did is, we just declared unified memory, and just to show you the difference of the code, we don't need anymore this QDMM copy, because when the FPGA writes to the unified memory, it's already in this memory. So we can just call the compute of the CPU, of the GPU. Okay? So we are saving this time, and we are saving all the different associated things. Few things out of that. First of all, we implemented some basic code doing some flow control. By just trying to do this, we were able to double the bandwidth between FPGA to GPU. It was mainly due to the way we coded things, but we were able to double the bandwidth between these two different things. The other thing is, as we are not waiting for the CPU to do some QDMM copy and so on, we are also cutting the latency by 2, which is quite interesting. And as I told you, for the FPGA, if we are using this or this configuration or this one, it will not change anything. You have nothing to redesign. So this is interesting because if you are using a GPU like the one on V100, which the one on AC922, you can use this because you have NVLinks. If you have a PCI Express, you will use this one because you have no unified memory, no coherency with the GPU, and it will not change anything for the FPGA. Two different things. So out of that, doing some flow control when you're acquiring some data is something which is harming the performance, as you can understand. Okay, so the idea is don't do the flow control in the data acquisition flow, but push it into the host memory, meaning that you are able to send all the data to write things in the host memory, and this CPU will manage the different queues and the buffers. He has nothing else to do. He has no computation because you have offloaded all the computation. So this is something which is very efficient. Let the FPGA card acquire the data, do all the processing online, and send them somewhere to the host memory. Sorry. The second thing is, well, as you are still using the CUDA driver on the CPU, well, as soon as you have everything in memory written by the FPGA, you can then use the pipelining, CPU threads, and CUDA pipelining if you want to have multiple processing. So all this can be really optimized once the data are in memory. I finished this one.
Thank you, Bruno. So the last part that we want to cover in this presentation is okay. So this was just ending the previous section. We can, for the computation acceleration, we can choose whether we want to concentrate on an NVIDIA using an AC922 machine, concentrate on T4 NVIDIA PCI Express attached on the coming machine that IBM will have in the portfolio. And also we can choose to process, let's say, muscles operations into an FPGA. So the last section that we will concentrate on is the compression. We had a very good surprising and interesting experience because both of us are, and with Fabrice, we are mainly focusing on CAPI and OpenCAPI activities and proof of concept. But we had a very good case which came from a customer who was really concentrating on their need to compress data. So we were then focusing for a few weeks on this acceleration capability that Power9 offers. And it's actually something that is embedded in any P9 processor, as it was in P8, but all the Sforza, Lagrange, and all the different families of P9 embed this compressor. So it's officially supported on IBM AIX operating system. So the customer was not interested in using AIX, he was working on Linux. So we had a very interesting time making some tests and to check whether we could support him using this Linux operation. And it took us very little time to discover that everything is ready, not officially published and supported, but it's working. So we obtained the promise that IBM will provide an official firmware, which will be an official firmware that you can install on the machine, that will offer you we'll see in a minute, the access to this compressor, which is available already when you purchase the power system on OpenPOWER system. So it's working efficiently, and the Fabrice is really the guy who did this interesting work, and it was again very surprising because we used one of our machines which was aimed at working on OpenCAPI, and we were able to have this machine working CAPI at this time, CAPI, acceleration, and also NVIDIA V100 co-processing. So the same machine was really, and this was for us the key for this presentation. We were just thinking that speaking about OpenCAPI and CAPI is fine, but since we are in IBM and we were lucky enough to have this opportunity to work on this compression, we said, okay, why not extend our presentation and come back to where we come from, that is providing servers which host all these very nice things together. So the patch that you need to apply for OpenPOWER is provided by IBM, of course. You need to patch the firmware, you need to patch the kernel, and you need to use a specific zlib library in order to compress things because zlib is really aimed at using the hardware capability, while gzip is not able to connect, let's say, software connect. I'm sorry, I come from hardware, but to connect to the gzip hardware capability. The result of that is that whatever you do with this will be compatible with gzip. So at the end, any end user can take your file and unzip it with its PC hosted software gzip. So there are several patches that you need to apply. We tested on 14.18. Good chance that everything is working here. We didn't test by ourselves, but it should be working on 4.19 kernels. And there are some explanations here that you can go. We need to use this zpipe and gzm libraries and compression stuff that is a little bit different from the standard gzip, but it's not a big issue. It's very easy to install. Fabrice did that in a very short time. So one good thing to see is Fabrice took a 1 gigabyte file, a 10 gigabyte file, and almost 100. Why not 100? Because he was using a RAM disk just to avoid suffering from the disk access. And what is very interesting is that we are observing that minutes are turned exactly into seconds. So that's very amazing. 2 minutes and a half become 2 seconds. So it's really very impressive, the fact that we can have this, from this kind of throughput, like few tens of megabytes per second, going to 5 gigabytes per second for the compression time, for the compression speed. Decompression is the same order of magnitude. We also used a customer-provided example. So we used his file, and he was actually very pleased because he knew his file. He was able to tune a little bit the compressor, saying, this is the type of file I'm providing to you, and he got even better results than the one we tested for him. So again, we spoke about the RAM disk. There are some details here, and then we can have a very short testimonial from the customer. So I don't tell you who is the customer, but you can have a look here, and if you are clever enough, then you might discover who we have been working for. Okay, so do we want to introduce this? Speaking about bandwidth, so let's take an example of an AC922. We should have 4 GPU attached to the 2 sockets. I just represented one, just because here we will fill the blank by the FPGA. So we have here the different bandwidths we can expect. In this case, the same, let's say the same hardware can provide 2 types of machines. So this machine is proposed in 2 options, and it was not clear sometimes for some customers. The top 500 machines or system clusters that IBM has won and confirmed this year are using the water-cooled 6 GPU systems. Okay, they keep the same name, but they are in 4 GPU water-cooled. In our case, we are mainly concentrating on the 1, 2, 3, 4 GPU system with same 2 sockets, and only 4 GPUs because water-cooled only. In this case, we have put here the different bandwidths we can expect for the different links. On this machine, on this AC922, you can add several CAPI2 attached, up to 3 CAPI2 attached boards that can offer you CAPI2 FPGA acceleration. You can also choose to use the second socket to host one OpenCAPI card, as Bruno presented before, with enhanced capabilities using this 3rd generation of CAPI connected cards. We have put here, I don't think it's very interesting to go into details, but we have put here the different bandwidths we can expect. One tricky thing to understand is that when we don't have the slide, but when we have 3 GPUs, they are sharing the bandwidth in between the 3 GPUs. When we have only 2, then we can enhance the communication towards the CPU. So there is a ratio, which is a 2/3 ratio. When you go from 6 to 4, we gain bandwidth. Okay, these are the metrics of communications between the different systems interconnected. These are for your information, the test that can be run to test this bandwidth, so you can have a look. What we want to show you through these 3 slides is the huge capability in terms of bandwidth that Power9 is offering. As a summary, we have been exploring the capability to host FPGA attached cards using unique CAPI or OpenCAPI capability that OpenPOWER systems are offering to you, with the coherency that Bruno explained to you, the fact that we don't need to copy the data, you work exactly on the actual data, no copy is required. The fact that we can share the memory, which is unique in this machine, between the GPU world and the FPGA world, as well as CPU world, obviously, and the capability to do another type of acceleration, which is well known, the GPU acceleration, and also another type of acceleration, which is related to the hardware compressor that we host in any OpenPOWER compatible system. So we have 2 types of machine. By the end of the year, we will have 2 types of machine. The one that is in this 6 GPU version used in Summit and Sierra Top 500 supercomputing system that IBM is very proud to have participated in. The AC922 offering very high GPU capability, unrivaled CPU to GPU bandwidth, and very excellent OpenCAPI solution to develop code now. We have a few universities and industries that are asking questions and developing on this machine right now. We should know that the CAPI and OpenCAPI capability in terms of port is limited, and the current firmware as a feature doesn't support to have OpenCAPI and GPU on the same socket. To counterpart these limitations, we will have this new machine that will be able to host more CAPI2 and OpenCAPI ports. Up to 4 OpenCAPI systems can be connected to the two CPUs. It still allows an excellent CPU to CPU and CPU to FPGA bandwidth, thanks to OpenCAPI, and GPU operation can be split into several PCI Express attached T4. So no V100 capability, no NVLinks in this machine, but we can largely enhance it's a very good machine to test FPGA acceleration. Whatever you were used to do into GPU, now we are encouraging you to test if you cannot push some acceleration, very basic computation into FPGA. So thank you very much for your attention. We have put here the 3 names of the Montpellier team. We are Fabrice is based in Montpellier, but Bruno and I are based in Nice. But we are very happy to share the server we have in Montpellier. We have open VPN access that we can provide to you for a few weeks for free, in order for you to test your code, or we can offer WebEx training, or we can visit you and establish a course if you need.